Hi, now we're going to discuss about physiological principles, especially respiratory system. So we will start to understand the concept of external and internal respiration. And also we want to define air volumes and flow rate that's happening in our lungs. So first of all, what is respiration? As a basis of human life, our respiration involves two ways. One is called external respiration, or we call it as a breathing. And the other is internal respiration. So external respiration means it is about transport process and inhaling oxygen from the air into our lungs and expelling carbon dioxide from lungs to the air. So this is exchange of gas in the lungs between the air and the blood that runs through the lungs. While we also have a concept of internal respiration, and that we call sometimes cellular respiration. This is more like metabolic process that cells consume oxygen and produce carbon dioxide and metabolic product. So this internal respiration means converting nutrients and oxygen into useful energy and produce waste in the cells. So this external and internal respiration are in fact closely linked, as external respiration provides oxygen to internal respiration and removes carbon dioxide that is produced by the internal respiration. I just have a table that explains it better, so I want to go over a little bit. So in terms of definition, internal respiration is metabolic process, while external respiration is a physical process. The nature of the process is external respiration is more like mechanical, while internal is biochemical process. And where does this respiration happen? Is internal respiration is at the cell level in the cell, while external respiration happens body and the environment that is in the lungs. So as a product, internal respiration produces energy and waste product, while external respiration involves in gas exchange. So let's consider about our lungs, which is external respiration system. So first, let's consider our lungs. We have a trachea, which is coming from our mouth or nose. And this trachea is so important that you can touch this and you will feel very strong, stiff ones. That is the cartilage in the trachea, because even when we are sleeping, this trachea should not fold because we need air exchange. So that's why trachea has a specific form with a lot of collagens to protect it from collapsing. And that one line of trachea separates into two, and that part, we call it as a bronchus. So it has a left main bronchus and right main bronchus. And then it goes down and down and down, and that has this bifurcating ways. You can see one trachea bifurcate, and this becomes a bronchiole, and this becomes terminal bronchiole. Up until this part, there's no actual gas exchange between the air and the body. So that is purely conducting zone. While from here, respiratory bronchiole, and then it gets down to alveolar duct. And the end part of this is so-called alveolar sac or alveolus. And this part is transition and respiratory zone. So from here, we can see the big lung has a lobes, and interesting, the right side of the lung has 3 lobes, while left side has only 2 lobes. That's probably because our heart sits here, which is a little bit on the left side. While when it gets down to this final business end, that looks like this. So bronchiole bringing air to alveoli, and there comes pulmonary artery and veins are meeting over here. So that looks like this circular globular structure that's called alveoli. And there's lots of capillary network to increase its surface area, and by diffusion, there's a exchange of oxygen and CO2. So those deoxygenated blood entering into the lung, this is pulmonary artery. And then after they get oxygenated, that blood leaving the lung and into our left atrium, which is a pulmonary vein. So this small alveoli is really small, and that is but a lot of numbers. So this a single alveolus line is called alveolus, and that's one of 300 million small sac-like units at the end of the last branches of the bronchiole network. So the diameter is only about 0.3 millimeter. That is tiny and tiny. And because the number is 300 million, we can calculate how big these alveoli compose as a volume. So that's, you can easily calculate like pi/6 times diameter to the cube and multiply by 300 million. That goes about even 4 liters. So our alveoli system composes most of our lung volume, which is even 3 to 4 liters. While these conducting zones, as conducting airway, is just purely passive conduit. And this still contains a volume, and that volume is about 150 milliliter. And what does that do in terms of gas exchange? No, it doesn't do anything about gas exchange. So sometimes we call this airway space as a dead space. We'll get back to this again. Let's consider about partial pressure of an oxygen. We know that oxygen composes of about 21% of this atmospheric air. So the atmospheric air, the pressure is about 760 millimilli Hg, or we can convert it into 1 atm or 1 times 10 to the 5th Pascal. So there are many ways to convert atmospheric pressure, but the oxygen composes only a fifth of this 760 millimilli Hg. So if you calculate, it's about 150 or 60 millimilli Hg that we denote as a partial pressure of an oxygen, P sub O2. And that becomes lower when it gets inside the lung alveolar space that is very moisturized. So it's saturated with water, and the oxygen partial pressure has to be lower because of the presence of water. And even that gets even lower when it gets into while meeting inside the cell or mitochondria, where they utilize this oxygen to produce our internal currency, which is ATP. So that part is even lower because inside the cell or mitochondria, we are continuously using that oxygen for producing energy. So let's think about how to measure this physiological capability of a human. So that respiratory. So when we get to the hospital for health checkup, you may remember you have done this spirometer, which measures lung volumes in individual. So how do we measure it? It's very simple. We have a pipe and we can inhale and exhale. And these chambers record the amount of volume which is proportional to what our lungs are doing. And nowadays we have more electronic ways to do this. So when we are breathing, breathing is part of a voluntary and part of involuntary. So involuntary way, we normally breathe this inhale, exhale while not paying attention. And that looks like a tide of the ocean. So this amount of volume, when we are not paying attention, we call as a tidal volume. So that volume change of the lung during our normal breathing. But also you can see when I have exhale, normal, but I realize I can exhale further. Let's do that. Till the end. So we can do this and then come back. Again, normal tidal volume. Inhale, exhale. And inhale, I realize I can inhale further. Let's do this. This is my limit. Okay, I can do this. And exhale. So this is our lungs capacity. Let's take a look. So our lung volume over time, this is normal tidal volume, which is about 500 milliliter. And I just did a forced inhale. So this is the limit I can do, and then exhale, normal tidal volume. And then while normally exhale, I exhale further, forced, this is the limit. So from this forced exhalation volume to the forced inhalation volume, and that we call capacity, vital capacity. So we define capacity as the sums of various volumes. And of course, even if I force my exhalation volume, there's some volume which I cannot handle, and that we call residual volume. So this one I cannot handle. So in this way, we can see from the real residual volume including and plus vital capacity is we can define as total lung capacity. And let's see. So functional, which means we can do this. So residual, when we have an exhale, so normal volume exhale, the amount of the air that's left inside the lung after expiration during normal breathing, there's this much amount that we call as during this functional and residual capacity. So functional residual capacity is really the summation of residual volume plus forced exhalation volume. So let's talk about ventilation. We're not talking about the ventilation of the air by opening the window, but we are talking about a breathing and physiology point of view. So ventilation is the exchange of air between the lungs, or particularly alveolus, and the atmosphere. So there's two phases of ventilation. First, air has to move into our lungs by inspiration. And then after this, we have to expire by moving the air out of the lungs during, expiration. So let's assume the flow rate is linearly proportional to pressure drop. So when the air flows in and out, this is a fluid movement, and we have to consider about the driving force. Driving force of the fluid is usually pressure difference. So that comes as delta P, and that pressure difference will cause the air to flow. So that flow can be represented as a flow rate here as V, a dot. That means a differential with respect to time. So the volume flow rate, and that there's a proportionality constant, which is we call as a resistance, meaning that for the same volume flow rate, the higher this proportionality constant, the higher the pressure difference we need. So this is R, and this R is the resistance to flow and the pressure drop. So to understand this better, we have to pay attention to the units. So the pressure drop as a millimilli Hg, you can use all other kinds of pressure such as a Pascal, atmosphere, but this is just an example. And the volume flow rate is a liter per minute. And then you can automatically know what are the unit of this resistance. So let's define the pressure difference, which is a driving force. This can be measured from the outside of the air to the inside alveoli, because we're considering the inhalation. So then the pressure is better to higher outside to inside. So that's a good definition. And then let's define the flow rate. When it comes positive is in, and when the flow direction occurs in the direction of decreasing pressure, that's more favorable. So that we call flow rate as a positive sign. And this is very similar to what we know from basic electrical engineering or circuit theory. So that an electrical circuit, you remember, probably heard about Ohm's law, which is related to the current flow with respect to the voltage difference or potential. That is driving force as an electrical potential. And if they go through a resistance, then those electric charge flow is defined as a current. So voltage difference is driving force, and that drives the current to flow, and that's proportional to electrical resistance, such as in this circuit. So here you can see the current is proportional to the driving force, which is voltage difference, but inversely proportional to the resistance. So the little the resistance is, the more flow with given the same potential or voltage difference. So it's time to try out your lungs airflow rate during your normal inspiration. So I already told that the tidal volume of normal breathing is usually about 500 milliliter or 0.5 liter. And why don't you test the number of breathing or respiration per minute? So you have a timer set up, and then watch your breathing, and then just count 1, 2, 3. So go ahead and measure your own number of breathing as 1 cycle per minute. So in general, your normal respiration rate is usually 12 to 20 times per minute. If you're out of this range, you may pay attention too. So in my case, I measured it already. It's about 16 inspirations per minute. So then what's my flow rate during my inspiration, which is, of course, the number of inspirations per minute multiplied by tidal volume. And you can have a cancellation out of minute, and this will give a 8 liter per minute. I think I have to remove this one. Oh, this minute is supposed to be 1 inspiration. Sorry about that. So during period between breath, inhale and stop and exhale. And that stopped part, there's no flow, which means from here, the flow depends on the pressure difference between the atmospheric pressure and my alveolar pressure. So when this becomes 0, that means the resistance is usually always positive. So my alveolar pressure, when it becomes the same as atmospheric pressure. So just make this concept simple. Let's define atmospheric pressure, because what matters is a relative difference, not the absolute. So let's set atmospheric pressure as 0. Then this is 0. Then alveolar pressure during the inspiration, which means the flow is coming from outside to inside. Then this minus should be positive because the outside to inside is defined as positive. So the alveolar pressure can be defined as a negative. Likewise, or vice versa, during expiration, the alveolar pressure should be positive so that it can go out, as we define the outside pressure as a 0. So in a nutshell, ventilation is driven by these changes of alveolar pressure, and that pressure is originated from the muscles of our respiratory system in our chest to create these pressure differences. So now we have determined our flow rate, and assuming the pressure drop during inspiration, let's say it's about 5 millimilli Hg. So delta P is 5 millimilli Hg, and we define the flow rate. Then we can also calculate the resistance. So if you do the math, you'll find out 0.4 millimilli Hg times milli per liter. So that unit is very important. Now, let's consider about this ventilation event, that our lungs are composed of this conducting conduit and the actual business end where gas exchange is happening. So this diagram shows clearly about what's happening. So let's say these dark ones are oxygen containing air when it goes down inside. So there are so many alveoli, so I just make a simplifying of big one alveolus representing our lung. So when it gets pre-inspiration and this part will get inside our lungs, then that part, except that part, the rest of this part will involve in gas exchange. So it becomes like this. After inspiration, the oxygen's gone. And you see this upper part, which is represents the conduit, so which does not involve gas exchange, will still remain there. And when you have expiration, then this will 3 units will go out, and we realize this one part will never be involved in gas exchange. And that I call as a dead space or dead volume, which means the volume of gas within the airways that does not contribute gas exchange during breathing. And we already know the volume is about 150 milliliters. So when we talk about ventilation rate, we can think of 2 kinds of ventilation, just considering the amount of air getting into our lungs or not. That's called total ventilation rate. But our interest is more on the ventilation which actually involves in gas exchange. So that we call alveolar ventilation rate. So how can you calculate total ventilation rate, which is number of breath and multiplied by tidal volume inspired per breath. Then usually for 1 minute, let's say about 15 breaths per minute times tidal volume of 0.5 liter. That will gives out about 7.5 liter per minute, meaning that in 1 minute, we actually get about 7.5 liters of air getting into our lungs. But what matters is that air which gets involved in real gas exchange. So that's actually meaning that not just this tidal volume, but remove that volume so that those core which is involved in gas exchange as a alveolar ventilation rate, that we should multiply by 0.35 liter as a new one, and we will get about 5.3 liter of air is actually involved in our inspiration for gas exchange during 1 minute of time. So does it make sense? Okay. So the next is, I think it's better to practice with the board exercise, which is alveolar ventilation and concentration of oxygen, because we care about this oxygen in the alveoli. To analyze this, we really need an engineering approach and system definition and system boundary, which we discussed previously as a mass balance, which is the accumulation inside this alveolar space over time. But over time, in fact, we are in steady state. So the accumulation is zero, is related to influx minus outflux, plus the net creation of oxygen inside this alveolar sac, which we know that there's no creation nor disappearance of oxygen inside the alveolus. So these terms will be zero. So we only care about the influx and outflux. So that we care volumetric flow rate of oxygen is in fact alveolar ventilation rate times fraction of oxygen volume. So we'll discuss about this. Thank you for your attention.